Good morning, students. So today we are here to discuss about lecture number 2 of kinetic theory of gases. So in this class already I had told you we are going to discuss about how we are going to get PV is equal to nRT for ideal gas. Okay. Before going to that discussion, initially what happened in 1803, okay, in the year 1803, John Dalton, name of the scientist, John Dalton, this person, that means this John Dalton discovered atom. Clear? He discovered atom. Next what happened? They came to a conclusion that matter is made of atoms. Matter is made of what? Atoms. Next what happened means, in the year 1873, kinetic theory of matter was proposed. That means initially it was treated as kinetic theory of matter only. Next, very specifically we had discussed this kinetic theory of matter for gases. That means it turned its name towards kinetic theory of gases. Why, I will tell you. Initially what happened, kinetic theory of matter, that means at the year 1873 we came to an era that we had studied kinetic theory of matter. But later what happened means, two scientists, basically Maxwell and Boltzmann, these two scientists worked heavily on gases, and hence this name changed to kinetic theory of gases. So what happened means, in case of solids, molecules will be very tightly bounded. Clear? In case of liquids also, molecules will be bounded but not as stronger as in the case of what? Solids. Next, in case of gases, what happened means, one molecule here means one more molecule will be very far apart from this molecule, and these will be having freedom to move anywhere. When particle is in motion means we are going to get what? Kinetic energy. That's why this theory proposed as kinetic theory of gases. Next, we had assumed that intermolecular force, okay, which we had discussed in our previous classes, that intermolecular force will be absent in case of what? Ideal gas. Okay, intermolecular force value will be absent in case of ideal gas. So why I am specifying on the word ideal gas means, ideal gas means an imaginary concept where ideal gas will be accepting all the gas laws. Ideal gas is nothing but what? It will accept, it is ready to accept all gas laws. Clear? So in ideal gas we had treated that intermolecular as well as interatomic force will be 0. Intermolecular and interatomic force is 0. That means negligible, absent in that manner. So intermolecular as well as interatomic force value will be equal to what? 0. And this is a assumption we had did. Basically this is nothing but what? Assumption. This is what? Assumption. We had assumed if it is like this means we can approach for better result. Clear? In that manner. Okay. Next. In kinetic theory of gases, in this chapter basically, we'll be discussing some average properties because we'll be having large number of molecules. For each and every molecule it will be behaving in its own manner. That's why we will be discussing here, or we will be studying average properties we'll be studying what? Average properties. Okay, now listen. Like example, average properties means in our previous class, that means in last class only I had told you mean free path. Mean free path means what? It is a distance mean free path. This mean free path is nothing but what? Basically it is a distance between successive collisions. Average distance between successive collisions, or distance between successive collisions. Now imagine that here we are having one molecule and here we are having one more molecule which is at this position, and here we are having one more molecule. So this molecule is going and hitting for this, let us suppose. After hitting, this molecule may change its direction. Let us treat in this direction it is moving, and after covering some distance it is going to hit for another molecule. This is nothing but what? Mean free path denoted by lambda, this letter lambda. Okay. Now after this collision it may come up to this point. Let us consider this as lambda 1, this as lambda 2. So if you generally see here means in this diagram, lambda 2 value will be greater than lambda 1 value. So lambda is nothing but, mean free path is nothing but average distance lambda 1 plus lambda 2 divided by 2. Lambda 1 plus lambda 2 divided by 2. Clear? So this is nothing but what? Mean free path. Next we are having one more characteristic, like what do we mean by relaxation time? Okay. So when we need that concept, at that concept only, at that time only I will discuss. So right now you just understand what is mean free path. Okay. Now let us go to our previous gas laws which we had already discussed. But this time we are discussing in detail, because in our previous chapters what all the things needed over there, that part we had discussed. But in this class, kinetic theory of gases, we are going to discuss gas laws. In that first one is Boyle's law. Clear? Same Boyle's law only which you had studied earlier, same gas law, that is nothing but what? Boyle's law. So what we had discussed, okay, in our last class what we had discussed, last classes I mean, Boyle's law means, what is the definition for Boyle's law? Listen, at constant temperature what will happen at constant temperature? Have you remembered? Volume of given mass of a gas is inversely proportional to pressure of that. Clear? 1 divided by P. So volume is inversely related with pressure P. Now, if we want to cross check how we are going to get the graph of this, that means P versus V graph, if I draw, means how we are going to get a graph. This is pressure P. Basically, this is our well-known y-axis. This is x-axis. This is volume V. Listen. Initially, at some temperature, let me call temperature as T1. At some temperature, let me call that temperature as T1. I am going to get a graph in this manner. This is nothing but what? This is nothing but an nature of graph for ideal gas condition. We are going to get graph in this manner. But if we perform experiment, means directly in laboratory by keeping constant temperature, how volume and pressure are related, means those values, if we plot a graph for this T1, means we are going to get a nature of graph in this manner. Clear? We are going to get a graph in this manner. This is nothing but gas we had considered for experiment, that is known as a real gas. And this is nothing but what? Ideal gas. Here red color dot indicates a real gas. Here also I had written with red color. This green color mark indicates for ideal gas. Ideal gas. Clear? For some temperature T1. Now second time what we did means, second time we had changed the temperature from T1 to T2 such that T1 is greater than T2. Clear? So when we consider in this manner, means we are going to get graph in this manner. Okay? This is graph for T2, this one was for T1. Now for lesser temperature, if we want to do experimentally how we had got this line, when we move for experimental part, we had got a nature of graph in this manner. This dotted line what we had got for T2, we had got in this manner. Clear? Here T2, this dotted line stands for a real gas of temperature T2. This red color dotted mark for real gas temperature T1. Now from these two analysis, that means from this nature of graph, finally what we understood means, finally what we can tell means, at very high temperature, that means this is for temperature T1, that means this curve, and this curve is for temperature T2 basically. And this is temperature T1 experimental, this is temperature T2 experimental. Clear? So what happened means, at very high temperature, that means among these two temperatures, T1 is high temperature. At high temperature what happened? This real gas as well as ideal gas values are quite near. Correct? That's why what we are going to tell here means, at high temperature, Boyle's law agrees with experimental, or we can tell that at high temperature, a real gas behaves as ideal gas. Real gas behaves as ideal gas, provided the temperature is high. At high temperatures, real gas will behave as ideal gas. Okay. And for low temperature, if temperature is low means real gas doesn't behave like ideal gas. Clear? Okay. Next, if we want to cross check equation of this means V is proportional to 1 by P means what we can write, PV is equal to constant, PV is equal to some constant, okay, or for a gas what we can tell, a P1 V1 is equal to P2 V2. Clear? So this is the case of, this is the story about what? Boyle's law. Shall we now go to next concept? Next we are going to discuss about Charles' law. Keep it in your mind, V is proportional to 1 by P. Okay, note it down somewhere because later again we need this expression. Okay, next. So next law we are going to discuss for next gas law, which is nothing but what? Charles' law. Next law we are having which one? Charles' law. Clear? So what this Charles' law informed us, that means what it stated for us means, this Charles' law informed that if a pressure is constant means, that means at a constant pressure, at constant pressure what happened, volume of given mass of a gas agrees with, that means this volume of given mass of a gas is directly proportional to absolute temperature. Volume of given mass of a gas is proportional to what? Absolute temperature T. So if we want to cross check a graph of this means, how we are going to get a graph in this manner? Okay, linear manner, correct? No, as V increases, T has to increase. Clear? Here volume, here temperature T. So we are going to get a graph in this manner. Okay. 1 second. Okay. In this manner we are going to get graph. This graph is for ideal condition, ideal gas. So if we want to do experimentally means, experimentally we are going to get a graph in this manner. This red color dotted line indicates what? For a real gas. Next, here just concentrate. If temperature value is increasing means, a real gas behaves as ideal gas, that means these two lines are meeting over there at high temperature. Correct, no? That's why here also what we can tell? Here also what we can tell? At very high temperature, real gas behaves as what? Ideal gas. Okay. At very high temperature, law holds good for all the gases. Or from this equation, V proportional to T means what I can write? V is equal to some Ct, where C is nothing but what? Constant, or V by T is equal to what? Constant. V by T is equal to what? Constant. Or we can tell that V1 by T1 is equal to V2 by T2. Clear? So this is the case of what? Charles. So in Charles' law what we had discussed, at a constant pressure, volume of given mass of a gas is proportional to what? Absolute temperature. And here also, at very high temperature, this real gas, red color dotted line for real gas, this real gas behaves as what? Ideal gas condition. Okay. So if we join both the laws means both Boyle's law as well as Charles' law, then what we are going to get? Let us check that pause. Okay. Now, from Boyle's law, we know that volume is inversely proportional to pressure if temperature is constant. Correct? Then, from Charles' law, what we can tell? What is the statement of Charles' law? Volume of given mass of a gas is proportional to temperature at pressure constant. So V proportional to 1 by P, V proportional to T means what we can tell from these two laws? We can tell that V is proportional to, here numerator T, denominator P means V proportional to T by P. Or if I remove this proportionality symbol means what I can write? V is equal to Ct by P. Okay. Or we can tell that PV by T is nothing but what? Constant C. PV by T is nothing but what? Constant. Or P1 V1 by T1 is equal to P2 V2 by T2. Clear? Shall we go to next part? So next we are having what do we know as Avogadro's law, Avogadro's hypothesis. Shall I erase this part? Okay. Avogadro's law. So what this Avogadro's law tells us means, initially in Boyle's law, what was the constant factor? Temperature. So Avogadro's also deals with in the similar manner, at a constant temperature, clear? And how this one Charles' law proceeded? At constant pressure. So here also at constant temperature and at constant pressure, that means in generally how I can tell, at constant temperature and pressure, at constant temperature and pressure, equal volume of all gases, equal volume of all gases contains equal number of molecules, contains equal number of molecules. At constant temperature and at constant pressure, equal volume of all gases contains equal number of molecules. So what is the meaning of this? Imagine here I am having gas 1. Let us consider that here I am having oxygen, here I am having methane. If in oxygen I am having, what is this? Let us consider here 1 liter oxygen I am having, here 1 liter methane I am having. So in 1 liter oxygen, if I am having 10 molecules means, in methane also, here also, in 1 liter I should have to have how many molecules? 10 molecules in that manner. Clear? So this is nothing but what? Avogadro's hypothesis. So shall we go to next part? What is the statement what we are going to discuss here? So V is directly proportional to, that means volume is directly proportional to number of moles. Clear? Where V is nothing but volume, N is nothing but what? A number of moles. So V proportional to number of moles means we are going to club all the three laws now: Boyle's law, Charles' law, as well as Avogadro's law. Can I just hold for a second? Okay. Now listen. So by combining, what we are going to get here means, I am going to get, from Boyle's law we are having what? V proportional to 1 by P. Clear? Next, from Charles' law we are having what? V proportional to temperature T. From Avogadro's law we are having V proportional to N. So if I combine these three means what I can write? V proportional to Tn by P. Okay. If I remove this sign means I am going to introduce a constant which is nothing but what? Gas constant R, and T as it is, N as it is, denominator P as it is. Just rearrange, we are going to get a PV is equal to what? nRT. PV is equal to nRT. So PV is equal to nRT means this is nothing but ideal gas equation. PV is equal to nRT. Here P stands for pressure, V stands for volume, N stands for number of moles, R stands for universal gas constant, T stands for absolute temperature. So this is nothing but what? Ideal gas equation, and how we got this ideal gas of equation. So keep studying. In next class we will be going to discuss what are assumptions basically. And one more point about ideal gas. Listen, characteristics of ideal gas is nothing but molecules of ideal gases are point masses. Okay, molecules are what? Point masses. So what do we mean by point mass? Means whole mass of a gas molecule is concentrated at very one single point, or we can tell that size of the molecule is very small, means that kind of molecule we are going to treat it as what? Point mass. And one more most general, as we had studied in thermal, not thermal properties of matter, in heat and thermodynamics, where we had studied that intermolecular force value will be absent in case of where? Ideal gas. This is nothing but what? Ideal gas equation. In case of ideal gas equation, intermolecular or interatomic forces values will be absent. Okay. So this is about today's class. So go through the concepts clearly. This is nothing but a Boyle's law. Okay. V is inversely proportional to pressure P. Okay. Next, V is directly proportional to temperature. Next, V is directly proportional to number of moles. This is nothing but from Avogadro's law. If all these three values, if I combine, means I am going to get V proportional to what is in numerator here in three terms, write it here. What is in denominator, write it here. Here numerator T and N, write it here. Denominator P, write it here. So proportional symbol I am going to equate this one. If I am introducing equal to sign means I should have to introduce a constant. Just rearrange and you are going to get what? PV is equal to nRT. And characteristic of ideal gas is nothing but molecules will be point masses. What is point mass? Mass of whole molecule. Okay, mass of whole mass of the gas molecule is concentrated at very one single point, and size of the molecule is very small. That is known as point masses, and well known general fact, that is nothing but intermolecular forces value, atomic forces value will be equal to what? As 0. So keep studying, please don't waste your time. Again in next class we are going to discuss what are assumptions to study kinetic theory of gases. Thank you.